Last time we covered convolution neural net. Today we're going to cover another type of neural network called recurrent neural networks and how it solved the problem in sequence modeling. So here we go. Sequential data, you see sequential data everywhere in your life. Many of the texts come in sequence, like a sentence or a paragraph or a book. We can see sequence come from in the form of audio, with the songs, a speech. It's a sequence, a wave in time. For example, you audio recording a 196 kilobit per second. Every second, they have 196 kilobit of data encoded into it. And finally, stock price, another great example for sequential data because it's happened over time, sometimes for a really long time. And it's very difficult to predict as well. Well, we certainly can try. So these are representative example of sequential data. And the sequence modeling problem is simply just given a certain data in the sequence, predict the next sequence or the next word in this sentence, right? So the example here is, I am comfortably watching this lecture at blank, and you're supposed to fill in at home. So we can use a fixed window for this. We can use maybe 2 words right before the word we need to predict. We're going to get these words and then trying to predict the next word. Right? So these are called fixed window. There's certainly problem associated with this sort of sequential problem. Number one is long-term dependencies. What happened is, say you can encoding the words before the prediction. So these words, lecture at, you can encode it maybe one-hot encoding. These are the one-hot vector represent the words. And then can you use these as sort of a feature to predict the next word, right? The problem with using only 2 words or a few words is you can't model long-term dependency. For example, this sentence right here, the coronavirus originated in China, and for a very long time description of what it is, and we should not call it the blank, right? So to use it, the, which is the 2 word before you had to make the prediction, is not enough info. We need information from the further distant past. The number 2 problem for sequence modeling is the word order, right? So from the last example, what if we say we use the entire sequence and put it all into a bag of words, right? So we say I can take the whole sentence here, put in the bag of words, and each of the words here will basically an index in this really long vector called bag of words. And if you see the word, you would highlight it at 1. If you don't see the word, that would be a 0. So this vector have lots and lots of 0 and a few 1s here. Well, the problem with this kind of encoding or kind of representation is that it does not reserve the order of the words in the sequence. For example, the food was good, not bad at all, and the food was bad, not good at all. These are very opposite sentence, but if you put in the bag of words, they basically end up with the same vectors. So the order, we need to preserve the order of the words in the sequence. And number 3 is about the model, about the parameter sharing, right? Say if we use a very long window for this, and we're gonna encode the whole sentence here and then trying to predict the next word. And you say you can somehow figure out a vector representation of these words and put them all into a vector. So what the problem of this, right? The problem of this is each of these so-called features are associated with the parameters. And right now, the way you put it in here in this whole vectors, the feature has separate parameter and they do not share across the sequence. What that means is if I am appear here and somehow is appear different places in the sequence, maybe and later on in the sequence, that would encode a very different parameters, right? So if I am appear later on, would that change our prediction? In theory, it shouldn't, but there is a need for us to share the parameter across the sequence. So it doesn't matter where the word appear, we still learn the same information. Right? So the sequence modeling criteria have a few criteria here. We should be able to handle variable length sequence, tracking long-term dependency, maintain the order of the sequence, and share parameter across the sequence. So all of this will be addressed by the recurrent neural net as an approach to solve this. So what is a recurrent neural network? Right? The recurrent neural network is just a network with a recurrent hidden node. So you see you have an input xi. Actually, first you want to predict some variable y at some time step t, and the way you do it, you have to process a sequence of features x by applying a recurrent formulation at every time step. So recurrent, basically, the output of one node is fed at input of the next node, right? In the same hidden node. So here's the formulation. You have a new state and the old states, and you're gonna use the old state to update the new state, and with some input at time step t, and we're gonna have a functions to learn the parameter w to transform from old state to new state, right? So you see here, we use the same function and the same set of parameter at every time step. So the hidden state contained by a hidden vector h of t here. And h of t is defined as the tanh function of the weighted hidden state of previous step and the input. Each of them associate with a weight vector, right? So w is a weight vector, and u is the weight vector that only associated with the input, right? You see here, so each of the arrow here have a set of weight associated to it. Now we also have a set of weight v to transform from a hidden state into the output, right? So v is a weight vector or weight matrix to do that. So that pretty much the basic formulation for the recurrent net. Remember the reason it's called recurrent, because its own definition contains its definition from a previous time step, and these are recurrent. Right? All right. So to understand the recurrent neural network better, typically people would unroll the recurrent into a sequence of network that share the same weight matrix, right? So they share the same weight, u, v, and w. But now instead of going back here, you just feed it into the exactly same node on the next time step. So you hear x0, x1, x2, and so on and so forth. So you can represent the recurrent neural network as a sequence like this. And the nice thing about this is this weight w are all share across the network. Same with v and w. Right? And well, you still have a loss function, same loss function to compare your predicted output and the actual labels, right? Actual label y. So how do you train this network? In fact, we actually applied the same concept as before to train in any neural network. So we use back propagation. So the step that I just showed you here with the arrows is forward pass, and backward pass is when you pass out the error gradient back to all the parameters, right? So this is denoted by the red arrows here, and you can see that pass it back, calculate the error gradient with respect to the output, and keep on passing back to the network with respect to a vector weight matrix v, with respect to the hidden node ht, and with respect to the weight w. And you see this information keep passing backward through time, right? So back from time t all the way to time 0, this error gradient. So that's why they call this training algorithms backpropagation through time, or BPTT. Okay, but the concept of computing gradient using gradient descents to calculate, update the parameters are all the same with this RNN compared to typical neural network. Now, there's one little problem with RNNs, is the length of the sequence. So what happened is when you calculate the gradient at this time steps, and you keep passing it back to the step behind, and this happened for a long, long time, the magnitude of the gradient over time would be deteriorate if you have it less than 1, or explode if you have it more than 1. And the problem is that if you need to make some weight update at the really early time step and you don't receive enough gradient, then there will not be enough information to update the weight, right? So the problem is, compute this gradient involve many factor of W, because each time you calculate this, you involve the matrix W or the derivative of it. So over time, keep repeating this gradient would be problematic. And you've seen this issue before with the exploding gradient, which is happen a bit less, but really damaging. Another problem is vanishing gradient, which is happening more time when the gradient is approaching zero, so there's no change in the weight. But that does not mean it learned something good. It just means that it just become really small. They couldn't make a significant update or meaningful updates. So what happened is these networks typically only capture short-term dependencies. Right. So what does that mean, short-term dependency versus long-term dependency? So if you have something that you can learn from to predict something immediately after, that's called short-term, because the thing that you're trying to predict very close or not far away from the thing that you have, right? So for example, this sentence right here, right? So standard RNN really just capture this kind of information, short-term dependency. Training an RNN on long sequence typically suffer from the vanishing gradient problem that we talked about earlier. So further back, the step has smaller and smaller gradients, and thus it's just not enough information to update the parameters. So it ends up that the whole training process only can produce parameters that can predict short-term dependency, or at least it only can update the parameter that closer to the prediction point. So the example here, if I give you a really long sentence ago, same sentence as before, COVID-19 originated from China and blah, 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 we should not call it the blank. And because this is the point you need to make prediction is too far away from this information where you need to use it, which is here, you don't have enough information, or the gradient is too weak to calculate it. So another funny example is, you can think about it as the memory problem of Lori in finding Nemo, finding Lori, that she couldn't remember anything past 10 seconds. Right? So this is a Lori problem here. Okay, you can tell I've been watching cartoon with my son a bit too much. All right, so you need to control the flow of the gradient, right? And in a article by Joshua Bengio, he proved that on the RNN should, in theory, be able to retain information by input through many time steps, but in practice, such long-term dependencies are very difficult to learn. And so one solution to this complex is that to use a bit more complex recurrent unit with multiple gates to control the flow information. And this gives rise to the idea of short-term memory cells, or LSTM. So let's talk about LSTM. Here's a standard RNN structure. You can see that just a simple 10 functions here, and taking input from the input and the previous state together, combine them right through this formulation, and then pass to the next state. That's as simple as this. We're about to make it more complicated with more gates, right? So right now, think about 10H is like one gate, right? So for the long short-term memory cells, proposed by Horst-Reister and Smith-Huber in 1997, it's had multiple interacting layers or gates that control the information flow. And we're going to go into these gates really quick. But notice the really cool idea of the LSTM structure is that it introduced the cell loop to produce a path that the gradient can flow for a long duration without go through multiple gates. So think about this is a path to pass from one cell to the next cell. This path are very smooth. It means like when you calculate the gradient, which is do partial derivative, and you pass it backward here, the information flow pretty smooth. Just got to go through this plus the point-wise addition and point-wise multiplication, which computing the gradient is pretty pretty straightforward. So you don't have to go into very complex function to calculate the gradient. Besides, calculate the gradient for this operation is a lot easier, and it flow very smoothly. So that's the reason why LSTM maintains its own self state. So beside the state of a hidden state here, it's also maintaining its own self state, which make the easy information flow. So the information will be added here or removed from the self state through these gates. We're going to talk about these gates in a little bit. And the gates let information pass through via a sigmoid neural layer. Think about it like a function, and some pointwise multiplication. Right? So you have a sigmoid and the multiplication. What happened here is, keep in mind, sigmoid gonna make the information whether 0 or 1 bitwise, and then when you multiply it, the one that have 0 get removed, the one that have 1 get continue. That's simple, right? So that's the core idea. LSTM would learn to do a few things. First is it trying to forget irrelevant parts of the previous state, and then it trying to restore relevant part to a long-term cell state. And it's also update the cell state, and finally it output the cell state whenever it is needed. Right, so we're gonna do a running example here, pretty easy example, but so say you have Bob and Alice are having lunch. Bob likes apples, Alice likes oranges, and then the next word is what is eating an orange, right? So you have to predict this word, right? So you can predict a she, or you can predict a he, right? Whichever make more sense, right? So let's try to figure out how this LSTM be able to predict the word she here instead of they or he, or whichever. Right. So first is the forget gate, which means to forget irrelevant information. And certainly this is the learn process, right? So you maintain a weight. So for each of these gates, you maintain their own weight. So the weight W associated with the forget gate is WF here. So what happened is you take input from the previous state and the output, and you multiply it with some weight vector, which you will learn through the process of backpropagation. And then you put it into a sigmoid function, but basically output either 0 or 1. So you say this determines whether it's going to be completely forget some information or completely keep those information, right? So for example here, if you do this and you have a sigmoid function, it might forget the gender pronoun of the previous subject, or Bob in this case, right? So that may be one information it decide to forget. Now the store gate would identify new information to be stored. And the store gate, it consists of a sigmoid function here and a tanh. So the sigmoid function was basically say that what value to update. Again, output 0 or 1, 0 mean don't store, 1 mean store, right? And the tanh should generate those vector value, just the same thing at the RNN in this case. So tanh should do the matrix multiplication between the previous state and the input. All right. So for this store gate may decide that, okay, the add gender of the new subject, Alice, that replaced the old subject, Bob. The third gate is called the update gate. And this is simply to combine information from the previous cell state coming in, right, with some forgetting. So this app T go in here, multiplication here, or multiplication here, meaning they're going to decide what information to forget. And also incorporate, or plus signs here, some information that you need to store and those values. You see what they're doing right here? It decides what to forget and what to store, or what to remember. Right? So this new C going to be the update cells. Right. So essentially that's what it is. Right? So example here will be actually drop the old info and added the new info about the subject gender. And then the last gate, the output gate, simply just output a filter cell state, right? So here again, we have a sigmoid function to decide what state of the cell to output, right? Again, to determine 0 bit or 1 bit. 0 mean don't output, 1 mean output. And the output will come from the current cell state, right? And it get through a 10H function to swatch the value between -1 and 1. And then you output with the hidden state T. Right? Remember, there is modifications here to filter out the version of the cell state. Okay? So, having seen the subject at Alice, the output may relating to a pronoun which is she. Right? So, we'll be outputting she. All right? Here, put everything together. The nice thing about this LSTM is when you calculate the gradient, again, the gradient gonna flow not in this bottom row with very complicated modifications and tangent and sigmoid, but it's flow up here. So one cell to the next, it flow back, and it should get through these plus sign and multiplication signs here. It make the gradient flow so much smoother and without interruption, would make the gradient stronger when you pass it back and to calculate, re-update the weights. Right? So that's essentially the core innovation of LSTM. Right? So in summary, RNNs can be used to solve sequential modeling problem. And the LSTM maintains separate cell state that use multiple gates to control the information flow and interrupted gradient. So the gates are forget, store, update, and output gates. Backprop used with LSTM can be done with interrupted gradient flow. And finally, there are better and simpler architectures and currently being researched. And want to mention quickly the rise of BERT in 2018, which will be covered in the next video. We'll see you then.